that up. All right, well, happy Monday. Welcome to Fluids. You should have received an email with feedback on your intro report that you turned in on Friday. Just some kind of brief comments on that. So the first chunk of it, I don't know, half, whatever. The first chunk of it is just kind of generic feedback that I gave to everybody so that you all have the same thing and I'm not like giving extra hints to one group over others. And then there's a second section that's specific to different things that I saw in your report. So hopefully that's helpful. Hopefully both sections of that you find helpful as you kind of dig into it a little bit more. I tried to pick out kind of key themes, a little bit of solution strategy, like how I would approach the problem a little bit in that first section. So make sure you read through kind of that feedback at least relatively carefully. So hopefully you find that useful as you kind of transition from this initial brainstorming part to actually trying to make something that works as far as your model. There are a couple new resources that I wanted to point out on the Moodle page with respect to this report, with respect to the design project. So if you look, there's kind of the stuff that was there, but then at the bottom of that section, there are a bunch of new resources. So in the feedback that I sent you, I kind of picked out two specific problems that I said, well, look at these problems, 6.68 and 8.137. There are other ones that we'll look at as well, but these two different ones, 6.68, if you pull up the solution, this is a turbine on a hydroelectric dam. So this is kind of right, you have to solve really both parts of this. You have to solve the water falling back down and the water getting pumped back up. So this is like half of that. Not actually, because this is using Bernoulli's equation, so this is assuming no friction losses, but at least gives you a place to start as you're starting to think about how to put this together. I think you'll see some of the things that they're talking about here will be useful as you start to think about how to build your model. The other problem, 8.137, this is, again, it's a different system, but this is a pump taking water from one reservoir and pumping it up to some other place up here. This is pumping it up into and just like shooting it out as a jet. But you can imagine this is kind of like the other part of your system where you're taking water from the lower reservoir, Lake Michigan, and pumping it up to your upper reservoir. This problem goes through into a little bit more detail because this actually has things like friction losses in it. It's not exactly solving your problem. It's obviously a little bit different, but a lot of the stuff here would be very similar to what you guys are thinking about. There are going to be, in addition to those two problems, there are going to be, hopefully by this afternoon, for sure by tomorrow, 2 more videos and like solutions that I post, or 2 more example problems that are going to potentially be helpful as you think through how to actually make up your model. So I'll go through and get 2 more example problems and solutions and post videos so that you can hear me if you want. If you're not sick of listening to me, you can hear me kind of talk through what I'm thinking and why. So hopefully that will give you a little bit of a good start as you think about putting this together. The other resources that are here, 2 videos just on kind of pumped hydro in general. Neither specifically relate to your project. It's more just so that you have some context for the thing that you're trying to do. One of the videos, I think it's the second one. If you're only going to watch one, that one was the cooler one in my opinion, because it actually goes and looks at a real system in Ireland. And I think when we're just like right? This is always the problem of like sitting in a chair doing engineering. You lose a sense of the scale of what you're actually looking at. So they go to a real pumped hydro plant and talk about, like, okay, when you open that valve and you let the water come crashing down, it's like an earthquake. Like the earth is shaking because there's that much water crashing down. And these are like little baby turbines. They're like, I forget, 70 or 80 megawatts. So relatively small on the scale of pumped hydro systems, but it's still like, you're talking about like metric tons of water per second type flow rates in a lot of these systems. They're massive. So I think it's fun to at least see a little bit of a sense of scale with some videos of like what do the tunnels look like and what do the systems look like. The last resource, there are 2 different links. Again, nothing that you have to go and check out, but I think it's kind of fun to at least spend a few minutes and play around with. This is a group from the University of Australia, New South Wales, I believe, that went through and basically did like a Google Earth map of possible locations where you could maybe put a system like this. So they have spec'd out, these are for 150 gigawatt hour systems all the way down to 2 gigawatt hour systems. So you can like look at where they would show up. And then they've kind of rated them. These are really good possible locations. These are like mediocre. But if you zoom in on any location, it shows, okay, this is like what the system would actually look like. Like we built a dam right here, and this is the upper reservoir, and it has some information on that, and this is the lower reservoir, this is how big it is, this is where it is, this is the length of dam that would need to be built in order to actually make that, this is how much excavation would need to happen. And then if you click on the middle, it tells you this is a class D, so this is like kind of a bad one. Relatively speaking, but this is how much, this is the head. So this is the difference in the height between the 2 reservoirs, and this is how much power you could get, and this is the storage that you would have for these reservoirs. So not as in depth as all of the calculations that we're going to be doing, but just to get kind of like ballpark figures for what's out there in the real world that you could actually do with something like this. And I think I don't know, there's the possibility for this to be a pretty large scale storage resource. So they've identified the other link is a little bit more about some of their methodology, but they've gone through and identified something like a factor of 100-ish, factor of 200 more good storage locations than we would actually need to be like 100%. That's our only storage technique. So you can be relatively picky and say, only pick the best of the best spots, make sure there's as little environmental impact as possible. But it gives you, again, kind of a sense of like, there are places out there that we could build things like this. So again, maybe gives you a little bit more relevance to the type of project that you're looking at. And there are places, a number of countries, including Australia, where this group is out of, that are looking at siting these kinds of systems and building them as a way to get larger energy storage capacities than you can currently with batteries. So these are things that are actually being built around the world and have been built around the world. So again, not that you need to spend too much time on any of those, but if you are interested to dive a little bit, those resources are there. Okay, the last thing to just mention, homework number 9. Homework number 9 is not due, it's due Friday. So if you want to do it by Friday, but it's going to be an extra credit assignment. So it uses a lot of the things that we're going to be talking about, things that you'll be doing in more depth as part of your design project anyway. I tried to make it a little bit different than, they're not going to be exactly the same types of calculations as the design project, but it's obviously on the same material. But if you do end up doing that, that's going to be worth up to 10 points extra credit, which again is about like 1% of your final grade. So it's not nothing if you do want to spend the time on that, but I'm kind of operating under the assumption that you're going to be spending more time probably on your design project. But that's there if you want to mess around with that, or if you want to do, you know, a couple problems, that's totally fine. All right, any questions on any of that stuff before we jump? So we'll get through probably not all of the stuff that we need to for you to like really dive in and have the design project like done today, but we should get through basically all of that by Wednesday. And then we'll shift gears again a little bit. So, all right, so what we're going to be doing today is picking up where we left off Friday. So on Friday, what we were trying to do is look at energy in pipe flow. We did that by defining like this control surface here and this control surface here, and we said, let's do basically Reynolds transport theorem, but instead of with conservation of the mass or with the momentum equation, let's do it with the first law of thermodynamics. And we went through the math a little bit, and what fell out of that and where we ended last time was somewhere, I might get some of the signs wrong from where you have it last written down, but we ended somewhere, let me just, so, and I'm just gonna say some of the variables here we also use in this class for different things, and we're gonna deal with the fact that I'm using the same variables for things that are different here, because we're like gonna then never use them again. So this Q doesn't mean flow rate. This is that's heat transfer, not flow rate. We use Q for flow rate. We'll always use Q for flow rate. We're gonna forget about heat transfer by like the next line of this equation. So, so plus W over m dot plus U2 minus U1. Again, those aren't velocities. That's internal energy, stuff that we talked about a lot in thermodynamics, stuff that we're not talking a lot about in this class, but those are the variables we would have used in thermo. Okay, and then we'll kind of forget about it, and U will be the X component of the velocity again, but for right now, we'll write it like that. This equals P1 over rho plus alpha 1 V1 squared over 2 plus G Z1 minus P2 over rho plus alpha 2 average velocity at 2 squared plus G Z2. Okay. So let's describe a little bit what these different parts of this equation are. So again, this is basically doing an energy balance on the fluid going in and fluid going out of some arbitrary control volume. So this would be right, we could have energy leaving or coming into the system by heat transfer. We could have heat going in, heat coming out. We typically aren't dealing with that in fluids class, but we could be. If we were, that's where it would show up. This is work. typically shaft work. That's how we would talk about it in fluids class. It's the same types of things here. Right, you can be putting in extra energy into your system by like a spinning, rotating pump, basically. So we can use something like that to be putting energy in, or we can use something like a turbine to be taking energy out. So we have to. That's a way that we could put energy in, take energy out. Or we could have the fluid change temperature, which would change the thermal energy of the fluid. So this is thermal of the fluid. And those are all things that we're not typically dealing with. The things on the right-hand side are the things that we've spent more time dealing with in this class. This would be the mechanical energy, at control surface 1. And obviously the same thing at control surface 2. Okay, so what our energy balance tells us is, okay, if we think about the right-hand side, the fluid comes in with some amount of energy, maybe things happen, and then it leaves with some other amount of energy. The difference in the energy that it comes in with and the energy that it leaves with could be a number of things. It could be like due to heat transfer, it could be due to a change in the temperature, or it could be because we like extracted work from the system. So that's what the left-hand side is talking about, the details of kind of where that energy change came from. We're going to basically take that whole left-hand side of the equation and compress it down into a single concept. And just call it's like the change in mechanical energy. Because we're typically dealing with and thinking about fluid mechanical energy, like velocity, pressure, potential energy. So we typically care about the mechanical energy that the fluid has. We don't typically care as much about the other kinds. So we'll compress all of that down into a single variable. We'll call it HLT. I'll define what that is in a second. And we'll say that is P1 over rho plus alpha 1 average velocity squared over 2 plus g z1 minus P2 over rho plus alpha 2 average velocity 2 squared over 2 plus g z2. Okay. So this is the equation that we typically will be using and thinking about. Okay. HLT is what we call the total head loss. So a positive number means that like that energy was lost, quote unquote lost. Energy can't be lost, energy is conserved. So what it means is like we changed from fluid mechanical energy to something else. So we lost fluid mechanical energy, right? Means that the energy coming out at 2 is less than the energy at 1. So positive means we lost, again, I'll put that in quotes because we can't lose energy. Lost fluid mechanical energy. And this is just a way to kind of track, when you're looking at it more from a fluids perspective, a way to track energy, because again, we're typically thinking and looking most closely at what's happening to the fluids, like pressure and velocity and height and things like that. And we care less about, hey, the fluid changed temperature by 0.2 degrees because of frictional heating. We're more interested in, like, that's energy that we can't use. So if the fluid changes temperature a little bit because of frictional heating, we can kind of consider that as lost energy, because we can't like then take that and use that to spin a turbine and get power out of it. We can't use that to pump the water up a hill or do whatever it is that we're trying to do. It's kind of lost to us as useful energy. We also can talk about, and this is kind of a discipline specific thing, capital H, which is HLT divided by gravity. So this is just the per weight head loss. This top one would be per unit mass. So per unit mass versus per unit weight. Again, it's kind of a discipline specific thing, whichever one is most commonly used. In this class, we'll most commonly use the top one, the per unit weight, per unit mass. Like how much energy do we lose per kilogram of fluid? So that's the one that we'll typically use, but you can just as easily use the per weight. Okay, so just so that it's in your notes, head loss describes how much mechanical energy we've lost and I'll write this, usually the thermal energy so it's usually like thermal energy because of friction, but we also could have taken it out because of like a turbine. Like we extracted it with some mechanism that's giving us work. So I'll just make like pump. A pump gives negative head loss because it's adding more energy into the system that wasn't there before. A turbine gives positive head loss because it's taking energy out. We're then like using it and doing useful things with it, but from the fluid's perspective, it's energy that was removed or taken out. So it's energy that was lost from the fluid. So that's really what head loss is describing. It's describing energy extracted from the fluid. We can use this concept to analyze complicated piping systems. We're going to build those more complicated models off of kind of an understanding of what happens in a simple case. So if we have, well, let's say this first. So we often will look at head loss as the sum of two different kinds of losses plus the sum, and I'll define these in a second. So this is the total head loss capital T, head loss total. Major losses and minor losses. So major losses are losses, friction losses, we're talking about, from normal flow down a straight section of pipe. So as you're just like flowing down a straight section of pipe, friction is constantly eating away from the energy that you have. You have frictional heating. Those are major losses. We call them major losses because usually that's the main component. Minor losses are losses from like bends, fittings, valves, etc. Basically anything exciting that's not just a straight section of pipe. So if you take a curve, that's going to look a little bit different, but there are going to be friction losses for doing that. And we'll look first at like the major losses at normal flow, and then we'll say, okay, how can we transfer that and look at minor losses from bends and pipe and fittings and valves and all kinds of different things like that. Okay, so we'll start by looking at major losses. I guess this isn't really an example, but major losses in laminar flow. And we'll look at laminar flow because laminar flow is easy and we can just figure out what these are exactly. So in laminar flow, we'd be looking at, say, a long section of pipe like this. It has some diameter. We know it's laminar because we said that it was laminar. So we know what the velocity looks like. It's going to be this parabolic shape. We've already solved this problem. And let's say we wanted to look at the losses between two different points on this long section of pipe. So let's say we wanted to look at, say, from control surface 1 there down to control surface 2, which is far away. Okay, that is some length of pipe. We'll call that capital L. That's how far we've gone. Our losses, our head loss, is equal to P1 over rho plus alpha 1 V1 squared over 2 plus G Z1. So that's the energy that we have coming in at 1, and the energy that we have leaving at 2 is P2 over rho alpha 2 V2 squared over 2 plus G Z2. Okay, so that's our head loss equation. We can simplify this a little bit because we know a couple things about the system. So because D1 equals D2, V1 is equal to V2. Our velocities are going to be exactly the same. This is a straight, constant diameter section of pipe. Conservation of mass says that has to be true. So that term and that term must cancel each other out. Velocity is the same. This is a horizontal section of pipe. We defined it to be a horizontal section of pipe because it makes our lives a little easier for this. So then the height at position 1 and position 2 are also the same. So our head loss is equal to P1 over rho minus P2 over rho, which is equal to delta P over rho. Okay, so what kind of energy are we losing? Well, we're not losing kinetic energy or potential energy, we're losing pressure. So as we're flowing along this pipe, pressure is going to be constantly decreasing. That's how we're losing energy. That's what friction's eating away our pressure. Okay, so how do we figure out what delta P looks like? Well, we can do that exactly. We've actually done that before. So let's just look up, at least pretend to look up equations that we've already figured out. So we know because you all have done it before, that the flow rate in laminar flow in a pipe is equal to pi r to the 4th over 8 mu times dp dx. You remember getting an equation like this in the homework? We can rewrite this as pi r to the 4th over 8 mu delta P over L. And we can do this because the change in pressure is linear. So what's the derivative of a line? It's just rise over run. So that's all that we're doing. Delta P over L, rise over run. So that's where we get our delta P. We also know Q equals average velocity times area. The flow rate is the average velocity times the area, which equals average velocity pi r squared. Okay, so what we can do is take these three equations, and I won't do it in tons of detail because it's not super exciting, but we'll take basically this equation here, plug it in for Q, and then rearrange and plug in what we find for delta. We'll rearrange it and then plug it in up there. We'll rearrange it delta P equals, and then plug it into the head loss equation. Okay, so head loss is 8 mu L V over rho r squared. Okay, so this is exactly what the head loss is for laminar flow. We found it, we built this up. This is all from like first principle models. There aren't assumptions or fits that like go into this other than like this is laminar flow in a pipe and this is what the head loss is. So the cool thing is we can find head loss exactly for laminar flow. We're gonna do a little bit of massaging to this and rearrange it so that it gets into a little bit different form, which will help us when we try to transition laminar flow and try to look at what's happening in turbulent flow. Okay, well, instead of radius, let's put this in terms of diameter. So if we want to do that, this would be 32 mu LV over rho diameter squared. Switching from radius to diameter, most pipe sizings are given by the diameter. So it's just kind of for convenience. Okay, so we'll put it in terms of diameter. Now let's look. Again, we have all of the right ingredients for a Reynolds number, but in kind of different places. So Reynolds number, which is always important for fluid flow, Reynolds number is rho V D over mu. So if you look, I mean, we have a rho, we have a D, we have a mu, we have a V, but they're kind of mixed up, some on the top when they should be on the bottom, and you know, they're not all in the right place. So we'll do some kind of creative algebra to pull out a Reynolds number from this equation, because we like having Reynolds number because it's important. Okay, so if we do that, we can pull out 64 over the Reynolds number. How did we get 64 from 32? Well, we have an extra factor of 2 that we'll pull out as well. L over D, V, average velocity, squared over 2. Okay, so we pulled out that extra factor of 2 to get like kind of a kinetic energy looking term, right? So this is the equation as you'll most often see it, but it's built directly from the Navier-Stokes equations, and from how we defined head loss. So this tells us for laminar flow, this describes all laminar flows. It gives us some insight. So describes all laminar pipe flow, every diameter, every Reynolds number, as long as it's laminar, this is the solution. This is how energy decreases as you go down this pipe. There are some interesting things that you can see from. It's a little bit harder to see in this this form of the equation, but you can see it kind of more readily in this top form. So head loss total, I think it's always useful to look at like what factors matter and how do they matter. Head loss is proportional to viscosity, length, and velocity. So if you double any of those quantities, you double the head loss. If you double velocity, all other things being equal, you double the head loss. If you double the length, that's maybe the most intuitive one. If it's twice as long, you get twice as much friction loss. If you double viscosity, you get twice as much friction loss. That's, again, maybe not that surprising because we see the same kind of thing with shear stress. Right? Shear stress, if you double viscosity, you double the shear stress, so you double the friction loss. And so we see some of these same ways that things matter. One thing that's maybe a little less expected, head loss is proportional to 1 over the density. So higher density fluids have less loss, which, if you think about it, maybe makes sense because, okay, so higher density fluid, that means for the same flow, it's going to have more inertia. So because it has higher inertia, it's going to have less loss. It's kind of interesting. The thing that's the most, or that kind of has the most effect on head loss, though, is the diameter. So head loss is proportional to 1 over the diameter squared. Diameter matters a lot. You guys all know this from, like, you know, anytime you've ever tried to drink a smoothie at McDonald's, right? When you have a normal size straw, it's really hard and you have to suck really hard and you hardly get any smoothie, but you use a little bit bigger straw and all of a sudden it's easy. It's because the head loss, like how hard you have to suck on your straw, how much friction losses your smoothie has in the straw, that depends on the diameter of your straw. And it's 1 over the diameter squared. So if you use a 2 times bigger straw, the friction losses goes down by a factor of 4. So you have to suck a quarter as hard to get the same amount of smoothie. Kind of fun, right? Who knew that fluids was so applicable to everyday life? So next time you're at McDonald's, get a smoothie and call it experiments. Get 3 different size straws maybe and see how hard you have to suck for each of them. But diameter matters a lot for how much loss you're going to be experiencing. And that's going to be true both for laminar flow. It's also going to be true for turbulent flow, where diameter matters a lot. We expect so this is like, we can build up a model for laminar flow from first principles. We can't do the same for turbulent flow. But what we can do is say we expect turbulent flow to be kind of the same. It's going to be different, but it's going to be like basic, some of the same types of factors. So we expect turbulent flow to be similar. So we get our model for turbulent flow. We're going to use a model to calculate the head loss for turbulent flow that's going to be similar, but not quite exactly the same. So it's going to be equal to this thing called F, which I'll explain in a second, times the length over the diameter, times velocity squared over 2. So you see it's broadly similar. In laminar flow, that first thing, F, would have been exactly 64 over the Reynolds number. In turbulent flow, it's not going to be exactly that. It's going to be something that's going to depend on Reynolds number, but not exactly, like, we're not going to get a nice, easy, neat equation for it. So F is the friction factor. It's a function. a function of Reynolds number. Just as it was in laminar flow. And laminar flow is a super simple function of the Reynolds number. It was just exactly equal to 64 over the Reynolds number. In turbulent flow, it's a function of Reynolds number, not going to be as neat and clean. It's also going to be a function of how rough your pipe is. Again, maybe isn't super surprising that the pipe roughness is going to contribute to friction. We're going to describe that as the roughness over the diameter. So this is pipe roughness over pipe diameter. So kind of a relative roughness. If you have a really huge pipe that's a little bit rough, that's different than a really small pipe that's the same roughness. Like the roughness matters a lot more in the small pipe than it does in the 10-foot diameter pipe. If you have a 10-foot diameter pipe that has like little tiny ridges, it doesn't maybe matter very much at all. But if you have a 1 centimeter pipe that has little tiny ridges, then those play a big role. So it's the relative roughness that actually matters. So what we do is determine or steps to determine friction losses. In turbulent flow, your first step is to calculate the Reynolds number. Then we can calculate the relative roughness, E over D. We calculate the Reynolds number first because if it's laminar, the roughness doesn't matter. If it's laminar, there is no roughness term. Pipe roughness doesn't matter. It's the shear of the fluid that's the only cause of friction. Then we find F. So we'll talk more about how we can find F in class next time. There are two different ways. One, we can use equations that people have built up, like correlations, which are not nearly as nice as F equals 64 over the Reynolds number. The other way that we'll be able to find F is through charts like this. So this is a very famous chart. It's called, we'll look at how to read this next time, but it's called the Moody chart, which is correlating the friction factor F with both the Reynolds number, which is along the x-axis, and the relative roughness, which is all of these like individual lines. So you can see kind of how this stuff, and again, we'll talk about exactly how some of this stuff works next time and how we would find F. And then we'll talk, this is just like for normal flow down a straight pipe, we'll talk about joints and fittings and valves and stuff, because that's just a pretty simple extension onto what we've done so far. So we'll talk about that next time on Wednesday. Until then, good luck. Have fun on your design project. Watch some videos of some pumped hydro places. Have a good Monday.